Hey everybody, let's review solving dynamics problems, making sure to cover both methods using Newton's way or this whole work energy way. So let's start with something straightforward. Let's say you just put a block on a ramp here, and then let's say there's kinetic friction between the block and the ramp, and we know the coefficient of kinetic friction. It's given. So let's say we're given the mass, the coefficient of kinetic friction, and that angle. What's the acceleration of the block? So what would you do? Free body diagram, right? There's a normal force, there's friction here, there's weight. Okay, so that's it, free body diagram. Pick coordinates. Let's say I'm going to pick my coordinates like this. Okay, so that's done. The geometry, here's the angle. Okay, now let's write Newton's second law. Decomposed. Okay, so the x component, I got mg over here, opposite, sine, minus friction, equals mass times acceleration, only the x component. Okay, y direction, n, and then the y component of this is adjacent to the angle, so minus mg cosine, equals mass times acceleration, only the y component. Since the acceleration is this way, in the x direction, there is no motion in y. So ay is 0, not always true, because of the way I pick my coordinates. Okay, and then we know that friction is proportional to normal force, like this, where this is the coefficient of friction. So then this can go here. So let me just jot that down. Sine theta minus friction right here, mu k n, equals mass times acceleration. This equation, n minus mg cosine theta equals 0, means n equals mg cosine theta, right here. All right, see this? So n equals mg cosine theta. Now I can solve for acceleration. Mass is non-zero, so I can cross it out. So the acceleration is this. Okay, so I got the acceleration. Now let's say the block slides this far, some distance d. Let's say it starts at rest, and it slides some distance d. How fast is it going here? Right, so look, the acceleration is constant, so we can use kinematics for constant acceleration. So which one of the formulas looks something like this? Where this displacement delta x is here. The acceleration is this. We started at rest, and so we're solving for the final velocity. Right, so that's 0, and then 2 times this whole thing times d. Okay, so this is the speed after the block slides some distance d down the ramp. So that's Newton's way to solve things. Let's try the same problem using the whole work energy way. Let's solve for the speed. So let's say it's a block here, it slides over here, some distance d. Okay, so work by non-conservative forces plus energy initial equals energy final. If there were no friction, then this would be 0. So there wouldn't be any work by friction, which is a non-conservative force, and then energy would be conserved. It would be constant. But because there's friction, we do have work by friction, which ruins our energy conservation. So first question, how much is this? So work by friction, let's just focus on that. Work by friction. When the block slides down the ramp, the displacement is this way. And then the friction would be opposing the motion. So the friction is this way, the displacement is this way. So work is this vector dot this vector. So when you dot them, they're just opposite of each other, 180 degrees. So it'll just be minus that friction times that displacement. Because it's the friction vector going this way, and then the displacement vector going this way. But when you dot them, you get a scalar. And because they're exactly 180 degrees, it's just minus. Because it's cosine of 180, which is minus 1. Okay, and then what is the friction? Mu k times n. And why don't we just recycle our work right here, where we had n minus mg cosine theta equals 0. So therefore n equals mg cosine theta. And mg cosine theta. And then I'll put the d right here. Or I'll just put, let me move this over. I'll put the d over here. Okay, so we got the work by friction right here. I'll just write it right here. Work by friction minus. Okay. Now, what is, let me move this to make some space. The initial energy here. So we're starting up here. So how much energy is that? What is the kinetic energy? We're starting at rest. So 0 kinetic energy. What about potential energy? Depends where we pick the datum. We can pick the datum here, or we can pick it here. Let's just make a choice. How about over here? So if the datum is down there, we're starting above the datum, this much. How high is that? Right, it looks like a triangle where this is h, this is d, this is theta. So sine is opposite over hypotenuse, so h is d sine theta. So we're starting with gravitational potential energy, positive, mg, h, which is d sine theta. Okay, and then that's it. There are no springs. Afterwards, now we're over here, going at some speed. So there is kinetic energy, 1/2 mv squared. And then gravitational potential energy, we're at the datum now. So 0. So that's it, we're done. So what's the speed? It's right there. So mass is non-zero, so we can divide by something non-zero, and then we can factor g and d, and then the 2 can go on that side. So we got 2gd sine theta minus mu k cosine theta equals v squared. So there we go. This is the speed after the block slides distance d. Let's compare it to what we got using Newton's way. See that? Same? It should be the same answer because it's the same physical process. We just use different methods to solve. Okay, let's put a spring in there now. So how about same problem, but this time let's attach a spring here. So there's a spring attached with spring constant k. Okay, and then there's friction. So, and let's say we know the coefficient of friction. Now, what's the acceleration when the block slides this way? So here's the free body diagram, normal force, friction. And if the block moves this way, the spring is displaced and it gets stretched. And the spring force opposes that displacement, right? So if the spring gets stretched down the ramp, the spring force is opposing that up the ramp. So I'll say spring force over here. Okay, and then there's the weight. And that's it. So I'm going to pick my coordinates and the geometry, the angles here. Okay, so in the x direction, we got sine, friction, spring force. So what is spring force? According to Hooke's law, spring force is proportional to, I'll just write the magnitude, the displacement. Right, the displacement. And then it's opposite. I already put the minus sign there. Right, I already drew the arrow going opposite, so we already got the minus sign. Because Hooke's law looks like this, with the minus sign. Okay, so if I put my origin, let's say right where the spring is unstretched over here, then the displacement, right, the displacement is like x minus the unstretched position. If I just make that 0, then I can just write the spring force is proportional to, like this, unstretched, but I'll just make that 0. So like this. This is the spring force. Right? It's proportional to how much the spring gets stretched. Equals mass times acceleration. Okay, and then in the y direction, mass times acceleration. There's no acceleration in y. Okay, and then friction is mu k times n, mu k times n. And then from this equation, n minus mg cosine theta equals 0, which means n equals mg cosine theta. Mg cosine theta. Okay, so then we can solve for the acceleration. Acceleration is, mass is non-zero, so I can just divide both sides by m. Okay, so we got the acceleration of the block, and unlike the previous problem, here, this acceleration was constant. This one is not, because here, the acceleration is a function of how much the spring gets stretched. So it's not constant, not constant. So we can't use kinematics for constant acceleration like we did in the previous problem. If we want to know, for example, when the block is over here, like it moves some distance d, now how fast is it going? We can't just use kinematics for constant acceleration. We would have to integrate this function. Right, so the acceleration is dv dt. So we can integrate this over time. The issue is this is not a function of time. This is a function of position. Right? So I'll write it like this. Acceleration is a function of position, not time. So how do we do this? We can't integrate this like dt. It's not a function of t. So here's a trick. So this is just the x component of this velocity. So dv dt, I'm going to use an intermediate variable, x. See the chain rule happen? dv dx, dx dt. It's chain rule. Okay, what is dx dt? The time derivative of position, velocity. dv dx dx dt is v, the x component of the velocity. So now look at this equals this. Okay, so let me just rewrite it. Okay, let's do separation of variables. See dx, I'll move it on this side. And then over here, that's the leftovers. Now let's integrate. Okay, see, so now we can integrate this function, g sine theta minus mu k cosine theta minus k over m x. We can integrate this dx, that's this, right? This is this. And then this is, just integrate that. And then we went from, let's say, 0 to d, and then from some initial to some final. Let's start at rest. Okay, so if we integrate this, times x minus k over m 1/2 x squared from 0 to d. Let me just put that substitution right there already. So from 0 to d, okay, and then on this side, v dv, so 1/2 v squared from 0 to final, although this is 0. Okay, so then I'll just move the 2 on that side to there, and then square root the whole thing. And then that's v. Okay, so that's how you would do Newton's way. Let's say you did this exact same problem energy way. So I'm going to go a little bit faster because it's very similar to the other problem we just did. So how much work is being done by friction, just like what we did before. So I'm just going to recycle that one. The work by friction was right here. The work by friction here. Mu k mgd cosine theta. Okay, so same as the last time we did it. Right, the friction, the work by friction from here to here, same, nothing's changed from the previous time we did this problem. And then initial, how much energy here at rest? The kinetic energy is 0. The potential energy depends on where we pick the datum. So last time we picked the datum down here. How about we pick it here this time, where it starts? So now the potential energy, gravitational potential energy is 0. The spring is initially unstretched, so that doesn't have any potential energy. And so then that's it. This is 0. Now final, over here, now the block is moving with some speed v. So it has kinetic energy, 1/2 mv squared. The spring is now stretched by some d. So the spring has potential energy, 1/2 k, however much it's stretched, squared. Okay, and then now gravitational potential energy, the block was here, now it's below the datum. Right? It's below the datum by this much. And that would be negative mg, and then h would be d sine theta. Okay, so if we want to solve for the speed, that's just right here. So let's pick these up and move it on the other side of the equation. So let me just do that. Minus equals. Okay, and then let's multiply everything by 2 on this side. Just go like this, and then 2 and 1/2, so that cancels this. And then let's divide everything by m. So divide by m, divide by m, divide by m, and here we go. And then we just take the square root. Let's see, I can you see there's GD, GD, I can factor that out. Okay, so v squared equals this, so v is the square root of that. All right, and then this is the speed using that work energy method. If you compare it to when we did Newton's way, same thing. Should be the same, right? Because it's the same problem. Okay, so I can post more of these example videos, so just so you can see the method and the comparison. So stay tuned for those, and I'll see you on those videos.